Hello there, and welcome to Science Before Bedtime, where curiosity nestles into the night like a distant star, finding its place in the vast cosmic tapestry. Tonight, we will be looking at the science of time and relativity. What is time? Time can feel like a quiet river flowing from yesterday, through today, and into tomorrow. In physics, time is often described as the progression of events from the past to the present and into the future. It is sometimes thought of as an invisible fourth dimension, alongside the three dimensions of space. You cannot see or touch time itself, but you can measure its passing as the gentle tick of a clock or the slow change of daylight. In one scientific definition, time is like the frame in which events unfold, giving order to sunrise, sunsets, and seasons. Think of it as a calm clock hand sweeping around a dial, steadily moving every moment. Scientists have pointed out that time always moves forward. It never runs in reverse. This idea is called the arrow of time. In everyday life, we mark time with seconds and minutes. The modern second is defined very precisely by counting oscillations of a cesium atom. Yet, at its heart, the nature of time remains subtle and mysterious. Even great thinkers like Aristotle and Newton pondered what time truly is. For our bedtime purposes, imagine time as the soft rhythm of our universe, steady, unbroken, and gently carrying us onward. Ancient concepts of time. Long before clocks existed, ancient people watched the sky and nature to tell time. Cyclical time was a common idea. The rising and setting of the sun, the phases of the moon, and the turning of the seasons reminded people that time comes in circles and cycles. For example, Hindu philosophy speaks of time as an endless wheel of time, rotating through ages of creation and renewal. Many cultures, Mayans, Chinese, Egyptians, based their calendars on repeating patterns in the heavens. Imagine ancient scholars watching a starlit sky night after night, noting that the stars gradually return to the same positions year after year. This gave a soothing sense that time flows in loops, like waves in the ocean that gently break and reform. In Egypt, people built the first clocks of a sort, sundials and water clocks. A tall obelisk or a flat stone carved with hour lines could cast a shadow, softly marking hours as the day passed. They split the day into 12 parts using these sundials, a clever, calm division of daylight. And when night fell, a steady drip of water in a bowl could mark the hours under moonlight. Indeed, An ancient water clock found in the tomb of Pharaoh Amenhotep was a precise instrument to track time after dark. Imagine the gentle drip of water echoing through a quiet temple, a softly measured heartbeat of night hours. Some philosophies saw time differently. In many Eastern traditions, time repeats in cycles, like seasons returning on a gentle music loop. In Western thought, influenced by biblical tradition, time was often viewed as a straight line from a beginning, such as creation, to an eventual end. Think of this as a sunrise that will one day become a final sunset without cycling back. Ancient philosophers like Plato and Aristotle tied time to the motion of the heavens. Plato suggested that time began with the movement of celestial bodies, and Aristotle said time is related to the motion of objects. In other words, watching the stars drifting overhead or the planets moving gave people a natural clock. These ancient views blended wonder with simplicity. Time was as natural as night following day, measured by the sky itself. Newtonian time versus Einsteinian time. For centuries, Isaac Newton's picture of time reigned supreme. In the Newtonian view, time is absolute and universal, like a perfectly still stream flowing at the same rate everywhere. No matter where you are in the cosmos, on Earth, on the moon, or on a distant star, a second is a second. Newton said it best. It is easy to conceive that time passes uniformly without relation to anything external. Imagine all the clocks in the universe ticking in perfect harmony, each second identical to the next. This was a comforting, gentle concept. Time is a constant beat underlying all of nature. Einstein revolutionized that idea. He taught us that time is not an unchanging river, but rather a flexible fabric woven with space. In special relativity, each observer has their own time, depending on how they move. If you ride in a fast rocket ship or sit still on Earth, your clock can tick at a different speed than someone else's clock. In practical terms, if you travel near the speed of light, your clock slows down compared to a friend's on Earth. So the once synchronized watches of Newton's universe can fall out of step. It is as if the river of time can stretch or slow in places, depending on motion. In everyday life, this effect is extremely subtle, far too small to notice in normal walking or driving. But at very high speeds, the difference shows up in experiments. Think of two identical clocks. One stays at home, and one zooms around Earth on a spaceship. The moving clock would actually record less time. It would fall slightly behind. The faster it goes, the more it lags. Einstein's equations tell exactly how much. A clock going near light speed must tick slower to keep the laws of physics consistent. So, in Einstein's universe, time is no longer a single melody that everyone hears. It's a lullaby that can be hummed at a different tempo by each traveler. The theory of relativity. Albert Einstein's theory of relativity comes in two parts. Special relativity deals with observers moving at constant velocity. It includes the famous speed of light limit, which implies moving clocks slow and lengths contract. An elegant way to say it is, space and time are fused together. Hermann Minkowski imagined all events in a four-dimensional space-time. Each event has a location and a time. You need both to specify it. This union of space and time means that how fast you feel time flow depends on your motion. Special relativity is gently summarized by the motto, "Matter tells space-time how to curve. Space-time tells matter how to move." No, that memorable phrase actually comes from general relativity. But even in special relativity, we see that the geometry of space-time governs how clocks and rulers behave. General relativity, 15, extends this to gravity. Einstein showed that gravity is not a mysterious force pulling from a distance, as Newton imagined, but rather the shape of space-time itself. Picture space-time as a stretched rubber sheet, a heavy ball placed on it, like a planet or star, makes a dent. If you roll a marble nearby, it curves around the dent as if being attracted. That's gravity. In nice words of physicist John Wheeler, matter tells space-time how to curve, and space-time tells matter how to move. In other words, the Earth orbits the Sun not because an invisible hand pulls it, but because it is gently following the curved path laid out by space-time. The effect of this curvature is subtle on Earth, but very real. For example, clocks in higher altitude run slightly faster because they are farther from Earth's gravitational dent. As one source poetically notes, if you set a precise clock on a mountain and another at sea level, the mountain clock will edge ahead ever so slightly over time due to weaker gravity. In satellites like Jeeps, the effect is strong enough that engineers must correct for it. In everyday imagery, imagine that every mass in the universe is a gentle indentation on the cosmic sheet. Everywhere the sheet curves differently, time itself can tick at a different rate. That's the dreamy picture Einstein painted, and it turns out to be how our universe really works. Time dilation. Explained, when we say time dilation, we mean that time itself stretches or slows down for someone moving or near a mass, as seen by someone else. There are two main kinds. First, special relativity time dilation happens at high speeds. If you travel in a rocket or simply move quickly, your personal time slows compared to someone standing still. For example, imagine two identical hourglasses. One is kept on Earth. The other is in a spaceship zooming through space. When they are reunited, the sand in the ship's hourglass will have trickled a bit less than the Earth hourglass's sand. The closer the ship's speed is to light, the bigger this difference becomes. Remarkably, this isn't just theory. It's been confirmed. Subatomic particles moving at high speed live noticeably longer, and ultra-precise experiments have measured that airplanes in flight or satellites carry clocks that tick differently than identical clocks on the ground. For example, astronauts flying around Earth in the International Space Station do age just a tiny bit slower than people on Earth. When they return, they have jumped forward in time by a microscopic amount. It's as if each astronaut took a brief dip in time. Upon landing, they arrived just a hair into the future compared to their twin back home. These effects are very small for everyday speeds, totally negligible for running or driving, but they perfectly match Einstein's predictions. The second kind is gravitational time dilation from general relativity. In a strong gravitational field, clocks tick more slowly, as seen by a distant observer. Think of this as if the heavy object is dragging on the fabric of time. A clock on Earth's surface runs a tiny bit slower than one on a mountaintop, simply because you are deeper in Earth's gravity. The closer you get to an incredibly heavy mass, the stronger this effect. Near a black hole, time would crawl almost to a halt. In fact, NASA scientists explain that time passes slower closer to the black hole than further away because of the intense curvature of space-time. Imagining sitting next to a black hole is mind-bending. To a faraway watcher, your clock would barely tick as you approach the horizon. So, in gentle terms, moving fast or being near mass, both make your personal time slow down relative to others. Gravity's effect on time. Einstein's insight that gravity warps time is one of the universe's gentlest secrets. The presence of mass, say a planet or star, creates a kind of dimple in space-time. Near that dimple, time itself is stretched. A helpful way to picture this: imagine time as the height of a peaceful wave, that ripples outward from a heavy rock dropped into a calm pond. The bigger the rock, the more mass, the deeper the depression in the water, and the slower the clock in that depression seems to tick for an outsider watching. In our world, this means a clock closer to a planet's surface runs ever so slightly slower than an identical clock far above. This curious effect has real-world verification. Atomic clocks have been flown in airplanes and rockets, and compared to clocks on the ground, they show tiny differences as predicted by general relativity. One example: if you kept a clock at sea level and another on the top of Mount Everest for many years, the mountain clock would get ahead by about 39 hours over the age of the Earth. That sounds like a lot, but remember it's over 4.5 billion years. Similarly, the clocks in GPS satellites, which orbit at high altitude, tick a bit faster than those on Earth, and engineers must correct for that difference to keep your GPS accurate. In the quietest terms, being deeper in a gravity well makes time pass more slowly. At the extreme end, near a black hole, this effect becomes dramatic. To an outside observer, someone falling toward a black hole would appear to slow down and almost freeze at the event horizon, the point of no return. This is because the gravitational pull so warps space and time that nothing can signal back. Practically, it means if you visited a black hole, purely hypothetically, and then compared notes later, you would say your clock ran at a trickle compared to the outside world. Closer to Earth, we experience a tiny bit of this on our planet, but close to a neutron star or black hole, the gentle warping of time is vast. Time travel in theory. The idea of traveling through time has long captured imagination. In reality, forward time travel is possible in a way. If you move at high speed or sit in a strong gravitational field, you effectively go to the future faster. As noted, astronauts in orbit are technically living in the slightly sped-up future relative to us on Earth. In everyday terms, though, these jumps are tiny, milliseconds or less, because we can't reach such extreme speeds. Going backwards in time, however, is much more problematic. Einstein's relativity equations do allow strange solutions like wormholes or cosmic strings, which, in theory, could connect one point in space-time to another. A wormhole is like a tunnel bending the fabric of space-time. If one could make the ends of the tunnel move differently in time, one mouth could open in the past relative to the other. If such a thing existed and were stable, big if, as far as we know it isn't, an explorer might step through and emerge at an earlier moment. But as many scientists caution, this is purely hypothetical. One famous paradox warns why backward time travel is fraught: the grandfather paradox. If you went to the past and changed something, say preventing your grandparents from meeting, you might erase your own existence. This kind of conflict suggests nature may forbid it. Indeed, many physicists believe that traveling to the past is impossible. Some imaginative ideas, like branching timelines or quantum worlds, try to resolve the paradox, but they remain speculative. In gentle summary, we can sail easily into the future by moving fast or waiting, but sailing back to yesterday seems to clash with the universe's logic. A calm constant in our experience is that time only moves forward. We never see ice cubes spontaneously assemble from water or broken cups leap back onto tables. Physicists call this one-way direction the arrow of time. Why does time have this arrow? One key reason is entropy, the measure of disorder. In a closed system, like the whole universe, entropy always tends to increase. It's like a sandbox getting more spread out and jumbled over time. Because entropy grows, the universe never naturally returns to a past, more ordered state. In simpler language, imagine rearranging a set of blocks on a table. It's easy to knock them into chaos, but nearly impossible to have them perfectly restack themselves without help. That loss of order is why time flows one way. The arrow of time is what separates yesterday from tomorrow. Even though the fundamental equations of physics work, if time were reversed, the thermodynamic laws give us a forward direction. As you drift toward sleep, remember, time's arrow flies gently forward, always toward tomorrow, guided by the quiet march of entropy. The nature of space-time. Einstein's wisdom was that space and time are really one unified fabric. This four-dimensional fabric is called space-time. To specify an event in the universe, you need to say where and when it happens. For example, here on Earth at midnight. This 4D view means that moving through space also ties to moving through time. One way to think of it: imagine a book where each page is a moment in time, and the three dimensions of space are on each page. We move from page to page as time flows. In 1908, mathematician Hermann Minkowski put this in beautiful geometric terms. The universe is a four-dimensional continuum, and time is intertwined with space. This was more than math. It was the foundation of relativity. In special relativity, two observers moving differently can slice this 4D loaf in different ways, so they disagree on when events occur relative to each other. But the combined space-time block is the same for everyone. Physicists often use space-time diagrams to visualize this. Imagine plotting every event like a star exploding, with 3 spatial coordinates and 1 time coordinate. In such a diagram, light always moves on a 45 degrees path because light speed is constant. What's profound is that light defines the fabric's ruler. Its speed links space and time. 300,000 kilometers of space equals 1 second of time on a diagram. This is why nothing can go faster than light. It would tip over the very axis of space-time. In curved space-time, general relativity, we can picture the geometry in a simple analogy. Space-time is like a soft rubber sheet. A massive object, like Earth, makes a well in this sheet. Planets then roll along the curved surface. The deeper the well, the heavier the mass, the more stretched the sheet. In exactly these stretched regions, time runs slower. This rubber sheet picture is just an image, but it captures the idea that space and time aren't separate realms. They are part of one peaceful cosmos, gently shaped by stars and planets. Beyond physics, time lives in our minds. Philosophers and psychologists note that memory and time are inseparable. Our brains give texture to time by forming memories. As one writer put it, time and memory are so intertwined that it's nearly impossible to disentangle one from the other. Without memory, each moment would be a blank slate, and the flow of time would feel meaningless. In fact, psychologists say our continuous sense of self arises from how we stitch past events into a narrative. Each remembered story anchors us to yesterday and shapes how we look forward. This leads to a curious experience. When life is full of new events, time seems to drag with detail. When days are repetitive, time feels like it flies. People often notice that as they grow older, the years seem to shorten. One reason is that young minds record many new experiences. First steps, first days of school, etc., while adults have more routine. Since our brains archive fewer new memories per day in old age, our days blur together. Studies even suggest that to a 55-year-old, a year feels about 5 times shorter than to an 11-year-old. In quiet terms, our subjective clock speeds up with age because memory making becomes rarer. Philosophers also wonder, is time ultimately real or an illusion? Some suggest that all of time exists together, eternalism, and we just experience a moving now. Others feel only the present moment is real, presentism. Whatever the deep truth, the everyday fact remains. Without memories, we wouldn't feel any passage of time. Therefore, our perception of time is as gentle a construct as our dreams. When you drift off under the stars, consider that your mind is weaving the night's moments into memories that will make up tomorrow's gentle tapestry. Time in the cosmos, black holes, light speed. On the grandest scale, time is woven into the cosmos itself. The universe has been ticking since the Big Bang, about 13.8 billion years ago. NASA notes that number from many measurements. Every star, galaxy, and atom in space shares this cosmic age. To imagine it, picture all of human history squeezed into the last few seconds of this timeline. We are but a blink at the end of a very long story. Knowing the universe's age helps us place our lives in a broader frame. As billions of Earth spins, our own sleep is a tiny, gentle wave in an ocean of time. In astronomy, we also meet the speed limit of nature. Nothing goes faster than light. Light travels at about 186,000 miles per second, about 300,000 kilometers per second. Even the fastest rocket or galaxy can only approach but never exceed this speed. As you lie beneath the night sky, remember that the starlight you see has traveled for years, decades, or even millennia to reach your eyes. We measure cosmic distances in light years. The distance light goes in 1 year, reminding us how vast and old the universe is. Black holes, as mentioned, are places where time itself warps extremely. Each large galaxy, including our Milky Way, harbors a supermassive black hole at its center. Near these black holes, gravity is so strong that space-time curls violently. A person near a black hole would see the outside universe's clocks race ahead, and an outside observer would see the person's clock almost freeze. While we can't visit one, we know from general relativity that a clock at a black hole's edge, the event horizon, would tick infinitely slowly to the rest of us. Finally, in an expanding universe, even time itself stretches. Observations show galaxies rushing away faster as distance grows. This cosmic expansion also carries a gentle rhythm. Cosmic time, since the Big Bang, is one dimension of our universe's history. The future of this expansion, and time itself, may be eternally distant if the universe grows forever, or something new if it were to cycle or recollapse. As you gaze upward in the dark, remember, the cosmos has marched on for eons, and its quiet breath is time itself flowing on. Time perception in the human brain. Within you, time is tracked by tiny biological clocks. The master clock is in the brain's hypothalamus, a region called the suprachiasmatic nucleus, CN. This SCN paces our circadian rhythm, the about 24-hour cycle of sleep and wake, of hormones rising and falling. Thanks to the SCN, your body roughly knows when to feel sleepy or alert, even if you hide from the sun. It uses light cues from your eyes to synchronize, so when dawn comes, your brain gradually wakes up. In effect, this brain clock keeps you drifting to sleep and waking in sync with day and night. But the brain has other ways of sensing time too. Neurotransmitters, the chemicals in our neurons, can make time feel slower or faster. For example, when your brain is excited, it might perceive moments as longer. Research notes that chemicals that excite neurons speed up time, while decreased firing slows down time perception. In simpler terms, when we are focused on many details, more frames of experience get recorded, and time feels more spacious. That's why a joyful, busy day seems full and long in memory. In contrast, when you're frightened or in an emergency, your brain records more memories per moment, which also stretches your experience of time. The amygdala, a fear center, becomes very active, etching events in high detail. After the fact, people often say, time slowed down during a scary event. It's not that clocks changed. It's that your brain's extra attention made the moment feel drawn out. Conversely, as we get older, we tend to encode fewer novel memories each day. Psychologists note this makes familiar days blur into each other. They explain that older people seem to perceive time as moving faster because fewer new memories are built later in life. In gentle terms, our mind's internal recording device adjusts the apparent pace of time. So within us, time is both steady and elastic. The SCN keeps the large cycles regular, but our perception of minutes and hours can bend. Tonight, as you feel heavy with sleep, note how still your inner clock rests, and how dreams and memories might alter your sense of passing moments. Sleep, dreams, and time. Sleep itself has a temporal rhythm. We cycle through stages each night, with roughly 90-minute cycles of light and deep sleep. During REM sleep, when most dreaming happens, your brain is active in ways that make time within dreams tricky. To many, dream time feels longer or warped. Some scientists have studied lucid dreamers, people who know they're dreaming and can signal it, to gauge how time passes in dreams. They found, interestingly, that some simple tasks, like counting or clenching muscles, take longer in dreams than in waking life. It's as if the dream state processes those actions more slowly. People often report dreams where hours or days seem to pass, but it was all in a few minutes. One gentle way to think about it is that our mind, untethered from the outside world, can stretch or shrink its internal timeline. When we remember a dream, it sometimes feels like a mini-movie marathon, even if we only slept a short while. However, scientists caution that dreams may not truly dilate time universally. Sometimes, dreams can also seem to play out in real time. Because we usually wake up just after a vivid dream, the early night dreams remain unremembered, giving the illusion that dreams happen near dawn. What about your sense of time right now, as you're dozing off? There is a familiar feeling that night passes quickly, perhaps because unconsciousness makes our time perception sparse. In reality, a night's sleep, even 8 hours, seems like nothing when we slumber deeply. If you've ever slept a full night and felt surprised that morning arrived so soon, that's the subjective quietness of night. Your circadian clock was doing its work, but your conscious mind was off the grid. As for dreams, let them gently carry you through moments that feel expansive. Even if you dream of roaming distant planets or reliving childhood days, trust that your body rests with regular cycles. Night and day still follow each other, and you will wake in the morning as naturally as the sun rises. The future of timekeeping. Humans have always strived to measure time more precisely, from sundials to mechanical clocks to quartz watches. Each step was more accurate. Today, the baton passes to atomic clocks, and soon to optical clocks. Modern atomic clocks use the vibrations of cesium atoms to define the second with exquisite precision. But even these have been outshone in recent years. Scientists are now building clocks based on light waves. These optical clocks use atoms like strontium or ytterbium that vibrate at optical, visible light frequencies, 1,000,000 times faster than microwave clocks. Because these atoms tick so rapidly, they divide each second into tinier moments. The result is truly staggering. The best optical clocks are now 100 times more accurate than the old standard cesium clocks. One famous example, a clock using a trapped aluminum ion, is so precise that if it started ticking at the Big Bang 13.8 billion years ago, it would be off by less than 1 second today. Imagine that. a timepiece so stable that over the entire lifetime of the universe, it loses or gains virtually nothing. Physicists are even preparing to redefine the second based on these optical clocks, the first update to the official second in over half a century. These ultra-precise clocks have practical importance. GPS satellites rely on atomic clocks, and without accounting for relativity, which shifts their ticks, they would be useless for navigation. Future clocks may be networked around the globe, comparing time like symphony conductors in harmony. There's talk of optical clock networks that could even detect tiny changes in gravity by how time warps across the Earth's surface. Some researchers dream of a nuclear clock, using transitions in atomic nuclei, which could be even more precise than anything today. So the future of timekeeping is bright and precise. Even as new clocks march forward, they still tick under the same gentle cosmic canopy. Every beat of these clocks, no matter how tiny, is synchronized by the same fabric of space-time they measure. With lasers and atoms, we will keep time down to the tiniest fraction of a second, but the sky above continues its slow turn regardless. Now, as you lie under the quiet night sky and let your eyes grow heavy, consider that everything you've heard is part of the same peaceful cosmic rhythm. Time flows like a river that carries galaxies and dreams, unhurried and eternal. Recall that the stars you see have shone for millennia, emitting photons that have traveled for years to reach you. Proof that time and space are vast and intertwined. NASA reminds us that the universe itself is about 13.8 billion years old, and yet each night feels so fleeting to a tired soul. Whether you think of time as an arrow or a wheel, it is a tapestry that enfolds you gently. Your heartbeats, breaths, and the cycles of sleep and awakening are all part of this time tapestry. In the hush of the night, let the soft rhythm of seconds and the silent march of galaxies lull you. Imagine the sky as a great clock face, each star a second hand moving imperceptibly. Tomorrow and every day that follows will come, as surely as the tides and seasons. For now, surrender to sleep and let time carry you. The universe's gentle pulse will keep beating while you rest, and when you awaken, the world will be ready to greet you with the same kind cadence. Sleep well under the starlit cosmos, at peace with the endless flow of time.